all-living toddler. It's all true. One to watch next Monday at 7:30.
Time, a fixed constant. And whilst some clocks might run a little fast or a little slow, highly accurate atomic timepieces monitor its passage with inscrutable precision. But imagine for a moment a world where time is fluid, stretched and twisted, ebbing and flowing like a vast ocean. What a strange world we would live in. Indeed, what a strange universe.
Welcome to Great Scientists. Tonight I'm going to be looking at a figure who is perhaps the most famous scientist of all, Albert Einstein. The scientists who'd been working up to 1900 had found laws that held pretty well for our solar system. But Einstein was the first scientist to look at the big picture, the entire universe. And what he was to find there was to be more amazing than he could ever have imagined.
Remarkably, nearly 50 years after his death, Einstein's ideas remain at the heart of cutting-edge scientific research. His theories, formulated with only a blackboard and chalk, were to change not just the development of science, but also the course of international politics. Not only that, but his apparently abstract ideas are used in guidance systems every time we fly in an aeroplane, whenever we watch a television set, or simply use a mobile phone. But in order to understand Einstein's work, we need to understand the world in which he grew up. Einstein was born into a period of political and technological turmoil. The expansion of the electrical industry in the early 1900s was having a profound effect upon the world, leading to thousands of new inventions. There was an explosion of new art and intellectual ideas, while many societies were about to disintegrate with the start of the Great War. Nationalism was on the rise, old certainties were collapsing, and with them, a new surreal physics was about to emerge in a world rapidly losing its moorings. All of this would have a profound effect upon Einstein.
Albert was born into a very close-knit, well-educated Jewish family, just as electricity was becoming big business. But he wasn't very good at school, as we shall see.
Einstein went to a Catholic school in Germany, where he was the only Jew. He disliked authority and described his teachers as sergeants and lieutenants. He was also a slow developer and a below-average student who was frequently disruptive in class. When, in 1894, his family moved to Italy, Albert was supposed to stay on at school. But after 2 months, he got a doctor's certificate to say that he was suffering from a nervous breakdown, and he was dismissed. He returned home without a diploma, and amid growing militarism, renounced his German citizenship. But eventually, he passed his entry exams into the Swiss Federal Institute of Technology. But once there, he annoyed his tutors and often failed to attend the lectures, preferring to study on his own. 3 years after graduating in 1900, he finally took a job at the Swiss Federal Patent Office, where he continued to study physics in his spare time. At the very beginning of the 20th century, Albert Einstein was working as a clerk by day and pondering the most abstract questions of cosmology by night. Just imagine the way his life must have worked at that time. Before Einstein, the concepts of time and space were dominated by Sir Isaac Newton, who believed they must both be fixed and absolute. But by the early 1900s, scientists were struggling to reconcile many of Newton's ideas with the new physics of electricity and electromagnetism. And one of the biggest problems concerned the speed of light. Scientists initially believed that light travelled instantaneously. But by 1880, the speed of light had been measured with great accuracy. And in 1887, two American scientists, Michelson and Morley, conducted an experiment to see whether the speed of light was affected by the motion of the Earth. However, after a protracted period of experimentation, they discovered the opposite of what they had expected. The speed of light was the same regardless of whether it travelled with or against the Earth's motion. It was described as the most famous null result in the history of physics. It just didn't seem to make sense. How could the speed of light not be relative to the motion of the observer?
Allow me, if I may, to elucidate.
Imagine I'm about to have a race with Einstein. Everyone who's been in a car will know that speed is always a relative measure. Now then, when both cars are stationary on the grid, my speed relative to the ground is 0 miles an hour. And it's also 0 miles an hour relative to Einstein's car. But once we start to race, obviously, our speed changes. But how can I measure my speed? Well, I have to measure my speed relative to something. Relative to the ground, it might be 100 miles an hour. But if Einstein is also travelling at 100 miles an hour in the same direction as me, then my speed relative to him is 0 miles an hour. And if we go in opposite directions, our relative speed will be 200 miles an hour. So why isn't the speed of light relative?
Light travels from the torch at 186,000 miles a second. Now imagine that this train is also moving at 186,000 miles a second. It should mean that, according to the normal laws of physics, the light would be coming towards me at 372,000 miles a second. But it's not. Every time anybody attempted a measurement of the speed of light, they always found that it stayed exactly the same. This problem was to torment Albert Einstein for 10 years and almost pitched him into a nervous breakdown.
I must confess that at the very beginning, when the special theory of relativity began to germinate in me, I was visited by all sorts of nervous conflicts.
Einstein imagined travelling at the speed of light. It occurred to him that it should, at least in theory, be possible to catch up with light. He imagined looking in a mirror while travelling at the speed of light. What would he see? Surely, if he were moving at the speed of light, then the light coming from his face wouldn't be able to catch up with the mirror. But if that happened, then wouldn't his reflection disappear? This seemed to Einstein to contradict basic physical principles, and eventually he concluded that he should be able to see his reflection. But if you can't catch up with light, because it always travels at 186,000 miles a second relative to you, then there must be something peculiar happening. Speed, remember, is distance divided by time. Einstein realized that if the speed of light were the same for a moving and a stationary observer, then each observer must be measuring different distances and times. Working at the patent office by day, Einstein wrote up his ideas in his spare time, and in 1905 published 3 papers in a German scientific journal. The first of these solved a long-standing question on the nature of light. The second demonstrated the existence of atoms. And the third, the special theory of relativity, merely changed our entire conception of the universe. Not bad work for a patent clerk. Einstein's theory was about to replace the idea of constant time and fixed space with the idea of a constant speed of light. In this way, he would blow our idea of the universe to pieces by asking a simple question.
Could there be something peculiar happening with time? Einstein had discovered that the speed of light was a constant. It was to be the end of the world as we know it.
By proposing that light always travels at a fixed velocity, regardless of the speed of the observer, Einstein showed that something strange must be happening with time. Not only that, but he showed that conventional ideas about the lengths and masses of objects must also be completely rethought.
At the time these equations were published, they were incomprehensible to most people on the face of the earth. And even today, they'll twist your brain around all kinds of peculiar corners.
Einstein's equations predict a number of strange phenomena. Perhaps the hardest to understand is that time, which we instinctively believe to be fixed and absolute, is in fact relative to the motion of the observer. This effect is called time dilation. And if you're wondering why you've never noticed it, remember, it's only obvious when you're moving close to the speed of light.
Let's watch a little more cinefilm, shall we?
So what is time dilation? Well, if 2 identical clocks are synchronized at the same place, and one of them is taken on a journey at close to the speed of light, when it returns, it will read less than the stationary clock. If this seems bizarre, bear in mind that this effect has actually been measured, and it happens because a moving clock runs more slowly than a stationary one. Einstein's prediction of time dilation also gives rise to what is famously known as the twin paradox.
I'm going to add a spaceman.
Imagine a pair of twins, one of whom leaves Earth in a rocket while the other stays behind. The rocket accelerates away until it is travelling close to the speed of light, on its way to a star 10 light years away. A light year is the distance light travels in a year, a huge distance. On the rocket, time will travel 10 times more slowly than it does on Earth. For the twin on the rocket, the trip to the star and back might take 2 years.
Terribly old.
But to the twin on Earth, the trip would have lasted 20 years. But Einstein's predictions don't just affect time, they also affect length. Imagine we're in a spaceship which is able to travel close to the speed of light, and we're looking at an astronaut flying past us in another ship. As we watch him, we notice he looks sluggish, as if he's moving in slow motion. And his cigar, although shorter than the one that we're smoking, appears to last twice as long. But to the other astronaut, everything in his ship seems normal, until he looks out of his porthole at us. We are moving past him at close to the speed of light. He notices we seem sluggish, as if moving in slow motion. Our cigar is shorter than his, but it seems to last twice as long. And according to Einstein's calculations, if we could reach the speed of light, cigars would become infinitely short and time infinitely long.
Remarkable, don't you think?
scientific community was slow to accept Einstein's revolutionary ideas, perhaps because they weren't used to the fundamental laws of physics being rewritten by a patent clerk in his spare time. Having just solved some of the deepest mysteries of the universe, Einstein applied for a job as a lecturer and was turned down. But after presenting his ideas to a conference in 1909, he was finally appointed to the post of associate professor at the University of Zurich. Over the next 10 years, Einstein would manage to produce an even more astounding theory. But first, let's not forget the most famous equation in the history of science.
E equals mc squared. Quite simply, it means that energy equals mass multiplied by the speed of light squared. But what does this mean? Well, it suggests that if we could break apart the atom, we could release energy of inconceivable greatness. In fact, this is the very energy that powers the sun.
Einstein showed that mass is energy and energy is mass. This means that if you could convert the mass of an average person's body into its equivalent energy, it could blow apart an entire continent. Einstein initially didn't believe it would be possible to release this energy, but physics was to move at a surprising rate, and this apparently abstract idea would eventually have huge scientific and political consequences. But first, Einstein was to publish an even more amazing theory, which would turn him into a household name overnight. Einstein had been bothered that his special theory only applied to a small set of phenomena, and he wanted to extend it to include acceleration and the force of gravity. After struggling with this problem, he eventually realized that gravity and accelerated motion are in effect the same thing. A simple example would be when we ride in a lift. As the lift accelerates, we feel heavier. This is because the effect of acceleration is the same as the effect of gravity. This insight paved the way for Einstein's new theory. By conducting abstract thought experiments and using what at the time were immensely complex equations, in 1915, after 10 years of intensive work, he finally completed his general theory of relativity. In it, he showed that time is actually part of the fabric of space, because, according to Einstein, time is not just fluid and relative to the observer, it even has shape.
Now, one of the remarkable consequences of Einstein's general theory is that space is bent and time is changed by the masses of the objects that occupy it. Now imagine that's a single photon, a single ray of light, and it's crossing space which is totally and utterly empty. Space which is geometrically perfect, like the squares on this sheet. It will pass across it in a perfectly straight line. On the other hand, what if there was a great mass occupying that space? A great galaxy, or even a cluster of galaxies?
Einstein showed that mass curves the space around it, and because of this, the path of a ray of light is also curved. In other words, light doesn't necessarily travel in a straight line. It can even go around corners. At the time Einstein published these ideas, Europe was in the midst of the Great War of 1914, and abstract physics was the last thing on most people's minds. But in March 1919, the British astronomer Sir Arthur Eddington led an expedition to Africa in order to test Einstein's theory by photographing a total solar eclipse. If Einstein was correct, the gravity of the sun should bend starlight, causing the stars close to the sun to appear in slightly different positions. Eddington exposed a total of 16 plates and sent them for developing. News of the result reached Einstein in September in a telegram from the Dutch physicist Hendrik Lorentz.
It said, Eddington has found star displacement at sun. Einstein was right.
This proof of Einstein's mind-bending theories, the significance of which few people could fully appreciate, came at the end of the Great War. At a meeting of the Royal Society, its president was moved to describe it as one of the greatest achievements in the history of human thought. The story made headlines across the world, and overnight, Einstein became internationally famous.
Now, there's a famous story about Sir Arthur Eddington, who led the English expedition to observe the 1919 eclipse. It was said around 1920 that Eddington was interviewed by a journalist who asked him a question. Is it true, Professor Eddington, that only 3 people in the world understand Einstein's theory of relativity? Eddington, it was said, looked at the journalist askance and asked, well, Einstein understands it. I understand it. But who's the third man? In the early 1930s, Albert Einstein was regarded as the most brilliant scientist of all time. He was a Swiss but a German by birth. And this is the time that Hitler is coming to power in Germany. Hitler hates Einstein. He hates him because he's Jewish. Einstein represents what Hitler and the Nazis see as Jewish science, abstract, mathematical, and without practical application. On the other hand, what the Nazis called Aryan science were things like engineering, chemistry, things with a practical application. And Einstein came to be seen as a particular figure of hate by the Nazis.
Einstein emigrated to America in 1933 and was awarded the Nobel Prize for his 1905 paper on radiation and matter, his general theory of relativity still being regarded as insufficiently proven. Although a lifelong pacifist, he urged the American government to build the atomic bomb, fearful that the Nazis would develop one first. And in 1945, the potential of his famous equation, E equals mc squared, became devastating reality with the destruction of the Japanese cities of Hiroshima and Nagasaki. Einstein died on the 18th of April, 1955. He spent much of his later life trying to find a unified theory describing all the forces of nature, but he never succeeded. But here, at the CERN Particle Accelerator in Geneva, scientists from around the world continue to explore ideas that have developed from his work, investigating ideas such as the Big Bang model of the universe and the formation of black holes. They continue to pursue Einstein's dream of formulating a unified theory which includes all the known forces. This vast machine, currently under construction, will eventually accelerate particles to almost the speed of light, flying them around 27 kilometers of cryogenically frozen circular pipe before smashing them to pieces. It's an extraordinary and complex process of investigation into the matter which makes up our universe, although it has been compared to dropping a watch from the Empire State Building and trying to analyze how it works by looking at the pieces. Einstein's ideas will eventually lead to new theories about our world. And whilst the development of science will continue to have a profound effect upon the way we live, it's sobering to realize that in many ways, the more we discover about our universe, the more mysterious it simply becomes.
Well, this is a story about a little galaxy, and every time its mummy gave it some gas, it got bigger and bigger until it became a big, strong galaxy, and it could fight off the big black holes. Don't put that in it.
A free set of information cards is available to accompany this Great Scientist series. To order yours, call our order line number on 0870 555 5055. Or you can also log on to 5.tv/factsheets.